Okay, so it looks like we're not going to have class next Monday. It looks like I'm going to have to be out of town. That's true for thermo too. I'm still going to be out of town at 10. So that's 10:14. And one thing that I would like to remind you, and maybe this is really especially true in thermo, but in both classes, the idea of these daily assignments, I'm giving you half the solutions or something, you know. So when you go through problems and you don't feel sure that you did it right, please ask me in class and we'll go through it. You know, like I'm planning on, you know, a chunk of this class being spent going through those problems. So yeah, just please do that. And I guarantee that, you know, questions you have about problems, other people have questions about that problem. So, you know, don't worry that everyone's like, oh my God, number 7. Couldn't do number 7. So maybe some people are, you know, some people are not nice people, but a lot of people are not thinking that way. Okay, let's do, well, anybody have any homework questions? Okay, let's do one more distributed load example problem.
I get number 7.
Did I tell you about the a friend of a friend was teaching math at a community college in Michigan somewhere, and the person came into his office hours and was like, I can't do number 7. I don't know if it was 7, but let's say it was 7. I can't do number 7. He's like, okay, well, can you show me the problem? He's like, no. It's not like this assignment. I can never do number 7, no matter what book, what assignment. And the guy's like, you can skip number 7s. So, and that solved the problem. Okay.
Yeah, I have a question.
Yes.
About the like a distributed load.
Yeah.
When it comes to trying to find like the like a distributed load, like the X component, does it matter what you use for like the I guess the triangle?
Yeah, no, it does not matter at all because all of our distributed loads are going to be acting straight down.
Okay.
And actually, it's hard for me to imagine a case where that would be relevant, even if the things were acting to the side. But so, like, if you have, you know, if you have a distributed load like this, and the centroid of that shape is here, you know.
Yep.
But this distributed load is acting straight down, which means the line of action is this. And so you can move that to any height without it affecting the problem. It's an equipolant system no matter what height you put it at.
Yep.
So no, it doesn't matter.
So like for I guess it was for like question number 6 also.
Mm-hmm.
What I did was I used to find the X component, I took the 2 to the space over 3 to find my X component.
Uh-huh.
Is that different?
Oh,
is that different than using like 2 space over 3 to find my X component?
Oh, no, it just depends what side you go from.
Okay. Oh, yeah, that's what I was thinking.
That's all, yeah. So you always are going, so on any side, there's always a point side and a wall side of the line, you know? And it's always a third of the way from the wall or 2/3 of the way from the point.
Okay.
Okay.
Does it also change depending on how you define your, I guess your origin? Or
well, then based on where your about point is, then you might have to. So we're going to do one right now where you have to fiddle with that a little bit. So let me set that up. So let's say we have a beam. And our distributed load looks like this. And let's say this is 1 meter, this is 1 meter, and the maximum value of that distributed load is, let's say, 1,000 newtons per meter. And I guess let's give it a weight to a mass. So let's say the mass is 30 kilograms. And we want to calculate those reaction loads. So free body diagram. At the pin joint on the left, bless you, we have a force vector, so I'll call that RA. At the center, at the roller, there's an upward force, I'll call that RB. There's a weight acting at the center of mass. That's 30 times 9.81. And then we have this distributed load. And that's a complete free body diagram. So now let's treat the distributed load like a point force. Okay, so we got this triangle. The centroid, we don't care about the y location of the centroid, but we know that the whole length of this triangle is 1 meter. Okay, so we know this is 2/3 of 1 meter from the point side. So this is 0.6 repeating to the centroid. And we know that the area of this triangle is the height times the base divided by 2, so 500 newtons. Okay, but now like you were just asking about, well, we know that the distance from the end is 2/3 of a meter, but that's probably not where we're going to put the about point. You know, like let's put it over here. That's where we normally would, and so now we're going to just have to do some subtractions and stuff to figure out what that is. We know that this distance is not drawn to scale. This is 0.3 repeating. Okay, and so to get from the about point to here, it's going to be 1 meter plus another 0.3. And so this free body diagram looks like we have this force vector RA. This is RB. We have a weight force of 294.3. And then we have a downward force here. Of 500 newtons. And this distance is 1.3 repeating. Okay, so you're often with those going to have to do some, you know, once you figure out where the centroid is inside of that shape, you're going to have to use that to figure out, you know, what the distance is from whatever your about point is. Now at this point, you always can write out a table, and I think it's safe to say that always in this class on tests and stuff, you'll have time if you want to go through the table, that's fine. I tend to think of these horizontal beams just in terms of distances and stuff, so I guess that's what I'm going to do here. So Newton's second law says RAX, RAY plus 0, negative 294.3 plus 0, positive RB plus 0, negative 500 is equal to zeros. And so right away we know that RAX is 0. There's nothing happening horizontally there. And then the second equation says RAY plus RB is equal to positive 794.3. And then the moment equation, my about point is here. So we have nothing from the force RA. It's 1 meter from the about point to both of these two, the 294 and the RB. So we have plus or minus 1 times RB. That's drawn positive, so would a positive, an upward force RB make this rotate clockwise or counterclockwise around that about point? Counter, yep, so that's a positive. And then we have plus or minus 1 times 294.3. Would that downward force make it rotate clockwise or counterclockwise? That would make it rotate clockwise if you're just imagining it rotating around that hinge. And so that's negative. And then plus or minus 1.3 repeating times 500. Would that downward force make it rotate clockwise or counterclockwise? Clockwise, so that's also negative. And so we have RB, and then that's equal to, these are both positive, so 500 plus, so that's 666.6. Plus 294.3. So 960.97. Okay, yeah.
For RB, is there any benefit to not always, rather than trying to figure out which direction it should be going, just always pick positive according to the coordinate system, and then
it is kind of helpful to do that. And later on, when we are thinking this way a lot, when we're doing internal loads, we're always going to put it all the way at the left like that. So
can you say that again? Put what? I'll put the...
Just always, I think what you're asking is always put the about point at the far end like that.
No.
Oh.
When you're trying to figure out which direction RB should be going, just always pick positive, and then if it's negative, it's going in the opposite direction of the coordinate system.
RB?
Yeah.
Did you say? Like whether that's going up or down?
Yeah, when you're trying to figure out what sign it should be, just always pick positive, and then it's matching the coordinate system. You get to just use whatever sign you
I would say, I mean, that's a roller, and a roller is just always pushing towards the body. So that's how I know that it's going that way, you know. And so then I know that this answer should be positive. You know, I know that the sign should be positive. I would always do it that way because there's no reason that rollers always have to be on a horizontal surface like this. They can be going any direction. So I would just always make it a pushing force toward your chosen body, and then the signs fall wherever they are. Okay, so we got RB, and so RA then is equal to 0 for X, and 794.3 minus 960.97, so negative 166.6 repeating. Okay. Any questions about that? Okay, so now we're getting into a new topic, And I consider this to be the sort of the heart of this class, the most important topic in this class. This is structures. So now what we're going to do is go from individual rigid bodies and calculating reaction loads to collections of rigid bodies connected by joints and calculating all those reaction loads. So this is a collection of rigid bodies connected by joints in static equilibrium. That's like the definition of a structure. So in parentheses, if it's not in static equilibrium, then you're not doing statics anymore. Then it's dynamics. And the collection of bodies is called a linkage. So any structure, if you took away one joint, say, or you took away one ability of a joint to control a degree of freedom, then that structure would be able to move and it would be a linkage. Okay. So this is something I want you to be sort of always have in the back of your mind. We're going to do this a little bit differently than you normally see in statics textbooks and stuff. I think there's good reason for this. But usually textbooks break up structures into two categories. Trusses and frames. The mathematical approach, is different depending on which of these two you have. Okay, so what's the benefit of doing this? Well, they have they're very streamlined methods for both of these two things. So especially with trusses, they reduce the number of variables and equations in your system quite a bit by breaking it up this way, So this way of thinking about it is efficient with variables and equations. And like always, like basically everything with statics, we've talked about this a few different times. In the old days, when you were doing everything by hand, reducing the number of variables was really important. But now with this huge amount of computing power on your phones and everything, it just isn't as important anymore. And so here is what you give up. So here are the drawbacks to that approach. So you gain this ability to do things more easily by hand. But the first drawback is you have to categorize the structure you have right, correctly. Or else everything just goes wrong from the start. If you categorize what kind of structure you have wrong, then it's wrong before you even start. Yep.
When you say trusses are efficient with the variables,
Yeah.
does that mean that you're able to do more problems with it that you wouldn't be able to do it the way that you're about to go into?
What it means is instead of a system of 15 variables and 15 equations, you have a system of 7 variables and 7 equations, which doesn't matter much to us, but it matters very much if you're doing it by hand, but through substitution or something, That's what it means. Okay, so the drawbacks are if you see something and it's a frame and you call it a truss, you can't get it right before you even start putting any numbers to it. Or I don't know what I was going to write. Everything is wrong. You can't do it. The second drawback is trusses and frames don't contain every possible structure. So there are structures and just to be clear, talking about statically determinate structures that can be solved through statics, so that are statically determinate. That can't be solved through either of these approaches. Okay, so that's a problem. Like some structures, like there's nothing wrong with the structure. You can totally solve it through statics, but you'd be out of luck with those two methods, So I'll give you one method that works for every statically determinate structure. And then I'll go back afterwards and talk a little bit about the truss simplification. It's a nice thing to be kind of aware of how it works so well. But this is really the thing, like, I want you to just get a lot of practice with this one approach that it's kind of like a brute force approach. You get more equations, more variables, but you can solve it easily on your calculator, and there's nothing you can't solve with it, and you don't have to worry about categorizing and all this stuff. Okay. So I'm just going to start with an example, and we're just going to kind of think our way through this. Okay. So let's think of a structure that's made out of two bodies, kind of the simplest structure you could have. Each of these two bodies are connected to the ground by a pin joint, and they're connected by a pin joint to each other. Okay, so we have a pin, and a pin. And just to be So I'm going to just, this is as simple as you can imagine, but I'm going to do one that you can't, that isn't a frame or a truss, just right off the start. Like, I'm not even putting any applied external loads on here. I'm just going to say each one of these two things has a weight. Yeah, I guess I'll put one external load here. So let's say we pull on it this way with 600 newtons. Okay, and we want to calculate the reaction loads at all of these joints. And this is not a frame or a truss. So as simple as this is, like using the two approaches that you would find in statics textbooks, you couldn't do this. Okay, but clearly it's a very simple, you know, it's not a complicated problem. And so just for reference, I'm going to call this body 1 and I'm going to call this body 2. And let's think about how we would do this. So, oh, and I'm going to name these joints too. Let's call this joint, this pin 1, this pin 2, and this pin 3. Okay. So the first thought we would have is kind of what are the different moving parts. We have a pin down here at 1. Okay. We have a member here, member 1. We have a pin here. We have a member here. And we have a pin at 3. Okay. And the loads that are happening, so think about what's in contact with what. The pin is in contact with the ground, right? It's in contact with that bracket. So we have some force vector here, and I'll call that the force on the pin by the ground. Okay, we're going to be using that double subscript notation all the time now. So remember that the first one is what the force is on, the body that it's acting on, or you can also think of that first subscript as what your free body diagram is of. And then the second one is what's applying that force. And we're ignoring, I guess, the mass of that pin. What other force is acting on this pin? What other thing is touching that pin?
Number 1.
Yeah, right. So here we have the force on the pin by 1. This we would treat as a particle. We don't control its orientation. You know, I mean, it could spin in there and it would still support the loads just fine. So all we would have here are two equations from Newton's second law. Okay. Now we go to the rigid body here. What loads are acting down at the bottom of member 1?
Might it be just minus FP1?
Yeah, that's perfect. So this is, so it's the force on 1 by the pin, or negative FP1. And then there's a weight force acting at the middle. I said that these each have a mass of 20, so this is 196.2 down. And then what about at the top? What force is acting on member 1? So I called that pin, you know what? Sorry to do this to your notes, but I'm gonna call I'm gonna call this pin A, pin B, pin C. And so if you want to redraw this, I'll give you time here. But this is the force on pin A from the ground. This is the force on pin A from member 1. This is negative FA1. Yeah, that'll work better. And now up here at the top, we have the force on member 1.
B1?
Yeah, right. So this is the force. It's on body 1. So F1 by pin B. Yep.
Would FA1 and FAD be the equal opposite?
Yeah, they're equal and opposites. Yeah. But we don't have to even notice that yet because that's just going to come out in Newton's second law, you know? But yes, you are right that's what Newton's second law will tell us.
Would it be better to write it as negative FA1?
No, it's better. We're just going to write out everything we know, and then we're going to go to the equations. Okay, and we're going to solve this big system of equations. Okay, is there anything else touching body 1? I guess I'm assuming that 600 Newton force is acting on the pin. So I'm going to say that 600 Newton force isn't acting on this. Okay. So that's it for this one. This is a rigid body, not a particle. So this is going to give us Newton's second law and rotational Newton's second law. This is a 2D problem, so this is 3 equations. Okay. And now we'll go to the pin B. What forces are acting on the pin B?
Negative 1B.
Yep.
600 Newton to the right.
Yep.
And we call it the FB2.
Yeah, exactly. So FB2, force on B by body 2. And how many equations are we going to get from this one? 2. Yep, that's a particle. And so we just get Newton's second law. That's 2 more equations. And now body 2. So we have the weight force, 196.2. What do we have up at the top here?
Negative.
Yeah, negative FB2. And what do we have at the bottom?
Brain shut off.
Force on 2, because we're looking at body 2. Yep, C. And the idea here is that this pin isn't touching the ground. The pin is touching the ground. Body 2 isn't touching the ground, I mean. Okay, so this is it. And how many equations do we get from this?
3.
Yeah, so we got Newton's second law and rotational Newton's second law. And that's 3 equations. And then the last one is the pin C. What forces are acting on the pin? Yep, negative F2C
FPG.
and F, right, perfect, FCG. And how many equations do we get from this?
2.
Yeah, 2 equations. Okay, so let's think about how many variables we have. So the variables are F on A by the ground, F on A by 1, F on 1 by B, F on B by 2, we already have 1B, F on 2 by C, and F on C by G. Okay, so 2, 4, 6, 8, 10, 12 variables. And how many equations? 5, 5 and 2, 12 equations. Okay, but that's a lot of variables and a lot of equations. So right from the start, I'm going to tell you a way that we might not occur to you right off the bat, but you can always make the following simplifications. Okay, we can keep this approach completely general, perfectly general. General. And simplify what we did above. And so here's what we're going to do. Assume every pin, and actually we'll do some that aren't pins, it's other kinds of joints. So we're going to assume that every joint is part of the lowest numbered member it touches. Okay. So let's go up above and figure out, you know, at each point, what the pin is going to be connected to. I mean, you can always lump bodies in with each other. You do that all the time, you know, like, I mean, everything you do is every rigid body we deal with is made of atoms and stuff, and you just lump them all into one thing. So we're just doing that here. We're just lumping the pin in with one of these bodies that it touches. And so this pin A would be part of member 1. Okay. What about the pin B? Would that be part? So it's touching 2 rigid bodies. Are we going to assume it's part of member 1 or part of member 2? 1, that's the lowest number member that it touches. Okay. And then C, what body is that going to be attached to? 2. Okay, so let's do it. So let's do it again with this approach. And by the way, the lowest numbered member thing, it's just bookkeeping. It's just to make sure that you're not double counting forces. This would work perfectly well with the highest numbered member or the lightest colored member or whatever, as long as you just have a way to lump it with one thing and not the other thing. Okay. And I just want to point out now that, I mean, you could have numbered these totally differently, right? And so so someone who numbered these rigid bodies differently would connect different joints to different bodies. The whole time through the problem, things would look different in your solutions, but at the end, you'd get the same answers. Okay. Okay, so.
But that makes grading just a blast.
Well, you know what I do is you're right that early on was a major issue. And so I started telling people, use this numbering, please. So we're going to do this again with the simplified approach. And I guess we probably won't we won't be able to do the numeric part yet, but we'll do that next time. Okay, so this time the pins are all part of a rigid body. So I'm going to go to, so I'm going to start with a free body diagram of body 1. Okay, down here, now the force between the pin and member 1 is an internal force. So that's, all we care about is the force that the ground applies to the pin. So I'm going to call that the force, you would call that the force on body 1 by the ground, or we can also just call that some reaction force because we're never going to isolate the ground, And then you have the weight force. And then up here, what external objects besides body 1 make contact with the pin is the question.
Body 2.
Yep, so there's a force on 1 by 2. And then there's one other force applied to the pin, the 600, yeah. This is a rigid body, so how many equations do we get out of this?
3.
Yeah. And now we'll go to the second body. Now remember that the second body doesn't have the pin attached to it. Okay? So that 600 Newton force is applied to the pin. That isn't applied to this body 2. Okay? The only thing that body 2 touches is the pin. Okay? So that means that here we have the force on 2 by the pin is body 1. So the force on 2 by 1 are negative F12. And that's it there. Any questions about that? Yeah.
Why doesn't 2 need contact with the ground?
Yeah, that's just at the top joint. You're right. I'm not done yet. So we still have the weight, 196.2 there. And yes, there's contact with the ground. So down here, I'll just call that. You could call it the force on 2 by the ground. I'm just going to call it RB. The only reason we need the subscript notation is to go from one body to another. So with the ground, you never care about that, because we never isolate the ground. And how many equations do you get here? Yep. And so 6 total equations. Can we solve it? We have 2 variables here, 2 more 4, 2 more 6. So 6 equations. Stupid computer. 6 equations, 6 variables. And so you can solve this. And so this way of doing it is pretty streamlined. It's the most streamlined you can make it with a total general approach as far as I've ever figured out. It's way better than 12. It turns out that, well, like I said, this is not a truss. So you can't use either the truss or frames approach to do this. If you did it without the weights, okay, if you were able to neglect the weights because say you had weights that were way smaller than that 600 Newton force, then this would be a truss. You could solve it with the truss approach. With this method, it would still take 6 equations and 6 variables. With the truss simplification, you could do it with 2 variables and 2 equations. So, I mean, that gives you a sense of how helpful that simplification can be in some instances, but this isn't so bad. 6 and 6 isn't so bad. Anybody have any questions right now? So I think I still have some distributed load problems that I can give you. So I don't think I have to give you any structure problems yet. On Wednesday, I'll finish this problem. We'll do some more example problems, and we'll just keep getting used to this approach. Okay, that's all.